Now let's look at one more example. This is the case where xn is equal to the sum of these sinusoids. Okay. So this is 1 plus sine 2 pi over capital N times n, 3 cosine 2 pi over capital N times n, cosine 4 pi over capital N times n plus pi over 2. Now you can see that all of these signals are periodic with period capital N. Okay, so overall, this signal has period, okay, capital N. So you hope to be able to represent this using a Fourier series representation using the set of harmonically related complex exponentials that have period capital N. Okay, so you hope to write this as summation ak e to the j k 2 pi over capital N n for k summing over one period. Okay, so to find these coefficients ak, we can again apply Euler's relation to split up these sinusoids. Okay, so this gives us 1 plus 1 over 2j e to the j 2 pi capital N n minus e to the minus j 2 pi capital N n, okay, plus 3 over 2 e to the j 2 pi capital N n plus e to the minus j 2 pi capital N n, okay, plus 1/2 e to the j pi over 2, because of this face pi over 2 here, e to the j 4 pi capital N n plus e to the minus j pi over 2 e to the minus j 4 pi over 2 over n capital N n. Okay. So if you compare this expression with the desired Fourier series representation above, right, you can see you can derive the corresponding values of AK, right? So in particular, A0, right, corresponds to the constant term, which is 1, right? A1 corresponds to the term e to the j 2 pi capital N n, right? And we can see that this appears here and also here. Okay, so we have 1 over 2j plus 3 over 2. Okay, and you can write this, moving j to the numerator, you have 3 over 2 minus 1 over 2j. Okay. Now for the term a minus 1, for k equal to minus 1, this corresponds to the term e to the minus j 2 pi capital N n, which appears here and here. Okay, so this, following similar procedures, we can write this as 3 over 2 plus 1 over 2j. Okay. Now looking at A2, A2 is the case where k is equal to 2. So this is e to the j 2 times 2 pi is 4 pi, right? E to the j 4 pi over capital N n, which appears here. So the Fourier series coefficient here is 1/2 e to the j pi over 2, right? E to the j pi over 2 is just j. So this is 1/2 j. Okay. So similarly, right, for this term, you get a minus 2 equal to minus 1 over 2j. Okay. So you can sort of see here that, similar to the continuous time case, you can observe that the Fourier series coefficients are, conjugate symmetric with each other, right? You can see that A1 is A sub minus 1 complex conjugate, right? Because there is this sign difference in the imaginary term, right? And A2 is equal to the complex conjugate of A sub minus 2, right? So, notice that AK is equal to A sub minus K complex conjugate. And when does this hold? Right, so you can show that, similar to the continuous time case, this holds when your signal xn is real. Okay, so this holds in general for xn that is real. Okay. Now, in this example, we see that each individual term has period capital N. So when you sum them up, the signal xn also has period capital N. Okay. Now, let me ask a extending question. Right. So what if the last term is replaced with cosine 3 pi over capital N plus pi over 2. Okay. So in this case, okay, so well, maybe I can ask somebody here. 对，庄敏勋在吗？
喂，有听到吗？
喂，嗨。所以如果说我把最后这个 term 换成这个 cosine 3 pi 而不是4 pi 的话，会有什么问题吗？
会多出一个讯号吗？
怎么说呢？
就是在用 builder 的时候会不能跟前面的合在一起。
OK， 所以你刚才说为什么不能合在一起？
我看一下。就是，好像不会。是它的讯号会数值会变吗？
我可以给一个提示，就是说，这个 cosine 3 pi over capital N 这个它的周期是多少？
周期，
它的周期会是这个 capital N 吗？
应该是。应该是。
OK， 就是你想想看，你如果说带 n 等于0，然后再带 n 等于大 N 进去的话，或许那不是一个很好的例子。就是说如果你带这个 n 等于1跟大 N 加1进去的话，你得到的值会一样吗？
不会。
不会嘛，对不对？OK， 好，所以这是有一点难的问题，对，所以就说这个一时间回答不出来是蛮正常的。对，我再看看其他同学有没有办法再进一步那个付晓彤在吗？
在。
OK， 所以刚才有提到就是说这个 cosine 新的这一项下面这一项它的周期就不再是大 N 了不再像上面这原本这一项是大 N， 那这时候怎么办？你还可以写成上面的这个形式吗？
不行。
不行，为什么？
我不知道
不知道 ，OK， 好，没关系。对，这个问题就是一个比较难的问题，所以小时候让大家回去思考一下这样。那我想其实关键就是在于说，你要能够写成上面的这个 Fourier series representation 其实代表的是你的这个讯号 xn 必须要是有周期大 N 的一个讯号因为它是周期大 N 的讯号，你才会用周期是大 N 的这些harmonically related complex exponential 去组成它。那现在如果你混两个 cosine， 它的周期是不一样的话，那你就必须要去找到它的共同周期。OK， 然后你的 Fourier series representation 就应该是以那个共同周期，也就是会是 xn 的周期去表示。OK， 所以这个大家回去练习看看。OK， 好，谢谢。OK。Okay, so right. So for this particular example here, we have this set of Fourier series complex Fourier series coefficients, right? For A0 plus minus 1 plus minus 2, okay, and the other within the same range of capital N values should be 0. Okay. So, right, if you okay, you can plot this out. You can plot this out, assuming here that we're looking at the case where the period is 10. Okay. So on the left-hand side, we're representing this in terms of its real and imaginary part, right? Because the Fourier series coefficient here are general complex numbers, right? We often split this into either into the real and imaginary part, or we express them in terms of its magnitude and phase. Okay. So, for example, when you're looking at A1, right? So A1 is 3/2 minus 1/2j, right? So you can write this as the real part plus j of the imaginary part, right? So in this case, this real part is 3/2, and the imaginary part is minus 1/2. So if you look at, A1, right, you can see here that A1 is 3/2, and the imaginary part is minus 1/2. Okay, and you see that these values, repeat themselves every period, right? So if you have a 1 at index 0, then you will also have a 1 at index capital N, 2n, and so on and so forth. Okay? Right. Now, you can also represent A1 in terms of its magnitude and phase, right? So you can write it as, the magnitude A1 times e to the j theta 1, right? Or you can write them out as, A1 cosine theta 1 plus j A1 sine theta 1. Okay? So in this case, A1, okay, is, square root the square of this, which is 9/4, plus the square of this, which is 1/4. So this is square root 10/2. Okay. And what about the phase theta 1? Right. So you know that if you take the imaginary part divided by the real part, you get tangent theta 1, right, which is the imaginary part divided by the real part. Okay, so this is minus 1/3. So therefore, theta 1 is minus arctangent of 1/3. Okay, so you can see here that this magnitude A, if you express in terms of the magnitude and phase, right? Magnitude A1 is this square root 10/2, right? And minus arctangent 1/3 is some negative phase that is less than pi/2, right? So it's this negative value here, and again, it repeats itself every integer multiple of capital N. Okay, so this is just utilizing this example to show you how you would illustrate the Fourier series coefficients when they are in general complex numbers. Okay. Right. Now let's move on to this very typical example of periodic square waves. Okay, so we looked at this exact example in continuous time, and now we're looking at this case for discrete time. Okay, so this signal takes on the value 1 from minus n1 to to n1 and 0, okay, everywhere else. But it repeats itself every integer multiple of capital N, right? So the period here is capital N. So therefore, for a signal that is periodic with period capital N, you can represent it as as its Fourier series representation using the complex exponentials with period capital N. Okay. And you can extract out the coefficient ak by taking the inner product between xn and the corresponding complex exponential. Okay, so in this case, xn is equal to 1 from minus n1 to n1. So the summation becomes a summation from minus n1 to n1 of 1 times this complex exponential. Okay. Now we can start out with the case where k is equal to 0. Right. So for the case where k is equal to 0, or any integer multiple of capital N, right, plus and minus n, 2n, and so on and so forth. Right, we have the coefficient ak equal to 1 over n summation of 1s, right? Because if k is equal to 0, the exponential is just 1. So we're summing over 2n1 plus 1 terms of 1 divided by n. Okay. To save space, let me write this up here. Okay. Now, for the case where k is not equal to 0 or plus minus n plus minus 2n and so on, okay, this ak, right, which is given up here, I can rewrite this by a change of variable to shift the summation, okay, from minus n1 to n1 up to 0 to 2n1 plus 1. Okay, so I do this by a change of variable where we set m equal to m plus capital N1. Okay, so if we do that, then this summation, right, originally from minus n1 to n1, becomes a summation over m from 0 to 2n1 plus 1. Okay. And then inside, I have this e to the minus jk, e to the minus jk, 2 pi over capital N. And now this n becomes m minus capital N1. Okay. Okay. Now I can then bring this N1 outside, right, because it has nothing to do with the summation over M. So I can write this as 1 over N e to the j k 2 pi over N and 1, okay? And then inside I have a summation from 0 to 2n1 plus 1 e to the minus j k 2 pi over capital N M. Okay. So here we have a summation over a geometric series. Okay, so by applying the formula for the summation of a geometric series, we can write this. Okay, we can write this summation as, 1 minus e to the minus j k 2 pi capital N of 2 capital N 1 plus 1, okay, divided by 1 minus e to the, so I'm sorry, I think this summation should be only up to 2n1, right? So that I have a plus 1 here, okay? And this is 1 minus j k 2 pi capital N in a denominator. Okay. So this is just applying the formula for the summation of a geometric series. Okay. Now just with a little bit of manipulation, right? So I want to bring half of this outside of the bracket. Okay. So let me bring half of this outside, which gives me e to the minus j k 2 pi capital N of capital N 1 plus 1/2 times e to the j k 2 pi capital N 1 plus 1/2 minus the same thing. Okay. And in the denominator, I want to do something similar. I bring out half of this. So I get e to the minus j k pi 2 pi over capital N 1/2 e to the j k 2 pi over capital N 1/2 minus e to the minus j k 2 pi over capital N 1/2. Okay. Right. So these terms cancel out. Right. These terms cancel out. And then inside here, when we take one complex exponential minus the complex conjugate of it, we get 2j, the sign of this face, and similarly in the denominator. So 2j canceling out from both the numerator and denominator, we then get 1 over n sine of 2 pi k n1 plus 1/2 over capital N divided by sine pi k over capital N. Okay. Right. So you can see that we get a formula that is a little bit like what we get in the continuous time case, right? So here we have, the ratio of two sinusoids, right, with different values of k depending on the index of the Fourier series coefficient.
老师，
哎，请说。
我可以问一下那个，就是最后一行那个分数，那个上面那个 sin 最后面那个符号是什么
sin 这一个吗？
对对对，
它最后
最后面那是
这除以大 N。
好好好。
对，
谢谢
就是上面这个。
哦。
对。
好。
它其实这个中括号里面就是上面这里。就是 by Euler's relation。我可以把这写成 cosine 加 j sin 嘛。那 cosine 因为相减的话就减掉了。对，然后因为这里有一个负的，所以减负的就变成又加了一次那个 sin 的部分，所以我其实是有 2j sin 这个 face。那下面也是我有 2j sin 下面这个 face， 那 2j 上下消掉，所以就会剩下这个样子。
了解，谢谢老师。
好 ，OK。Right, so here we have the ratio of two sinusoids, okay? Now you can sort of view this as samples of sinusoids at, integer multiples, right? If you view k, different k values as different integer multiples of this n1 plus 1 over 2 over capital N, right? And in the denominator, this is sampled at integer multiples of 1 over capital N. Okay. So as capital N increases, right, suppose that, your period increases, meaning that these periodic square waves are separated more and more apart. You're sampling these sinusoids at a denser and denser rate, okay? So for a larger period, for a larger capital N, these square waves are more separated in time. Right. But if you look at the Fourier series coefficient, you would be, equivalently sampling these sinusoids at a faster and faster rate. Okay. So we actually have a couple of examples here. Right. For all these examples, we're setting n1 equal to 2, but with different periods. Right. This is n equal to 10, n equal to 20, n equal to 40. Okay, so you can see that as this period increases, right, you're sampling this ratio of sinusoids at a denser and denser rate. Okay. Right. Now, if you recall, in continuous time, there was a lot of argument between mathematicians about whether or not you can use a Fourier series representation, basically a linear combination of complex exponentials, to represent a discontinuous signal like the periodic square wave. Okay? So in continuous time, we showed that, by Michelson's observation, you see that if you use a truncated Fourier series to approximate a square wave, right, you will get something like that looks more and more like a square wave, but there continues to be, small ripples above and a spike at the edge by 9%. Which we call the Gibbs phenomenon. Okay, and you would need, the number of terms, right? You would need the summation over, these Fourier series to go to infinity in order to well approximate this square wave. Okay, but in discrete time, this is not an issue. Right? In discrete time, we already showed at the very beginning that, no matter what is the value of x, as long as, it is periodic with period capital N, we will be able to perfectly represent it using its Fourier series representation. Okay. Now you can sort of observe this for the square waves here. Okay. So suppose that we again take a truncated Fourier series representation like we did in the continuous time case. Right. So instead of summing over, capital N consecutive values, suppose we sample, we sum over a smaller range from minus capital M to capital M. Okay. So here we're assuming that the period capital N is odd. Okay, it's odd. Now, if it is even, then you just sum over an even number of terms, right, going from minus M plus 1 to capital M. Okay, but this is not that critical for our discussion. Okay, so suppose that in the discrete case, we'll also look at this truncated summation, truncated Fourier series representation. Now, if you take capital M equal to 1, right, you would get something that looks like this. Okay. Now, if you increase M to 2 terms, to 3 terms, you will see that you get something that looks more and more like a square wave. And eventually, when you increase capital M to 4, you get back exactly the square wave. Exactly the square wave. Okay. So here we're looking at the case where N is equal to 9 and 2N plus 1 that is equal to 5. Okay. So when M is equal to 4, right, you're summing from minus 4 up to 4, which is 9 consecutive index values. Okay. So 9 consecutive terms is sufficient to represent perfectly a periodic signal with period 9. Right. So you can see that, indeed, right, as we increase M from 1 to 3 to 4, we eventually are able to perfectly reconstruct the square wave. And this is done without, any convergence issues. Okay. So we do not have this overshoot given by the Gibbs phenomenon, and we do not require, infinite summation to push this, this peak to the discontinuity point. Okay. So there is no convergence issue. Okay, which we call the Gibbs phenomenon, right? Or say there is no okay, and this is true in general, right? Not only for periodic square waves, since xn is completely specified by a finite number n of parameters. Okay. So this is in contrast to the continuous time case where we need to take the summation over infinite terms, right? So for continuous time signals, you would require infinite number of parameters, right? Infinite number of these Fourier series coefficients in order to well represent your signal. Okay. So, right. So I didn't get to where I wanted to get to, but what we wanted to talk about next is the properties that we can derive for discrete time Fourier series, like what we did in continuous time. And, go back to the very beginning where we talked about why we want to represent signals in terms of linear combinations of these complex exponentials. Okay, so the main motivation for this is that these complex exponentials are eigenfunctions of linear time-invariant systems. So if we can represent signals in terms of linear combinations of complex exponentials, then we can also easily obtain their output in terms of linear combination of the same complex exponentials.